Sir, good morning, sir.
Good morning, Reddy Garu. How are you?
Fine, sir. Fine, sir.
Good to see you for
How
a
do
long
you do,
time.
sir?
Good, doing good.
Yeah, I just introduce you, then so you can take up the session, sir.
Okay.
Very good morning to all. Welcome to the second session of 3-day online FDP on sustainable engineering. Now we have here Professor Sudhakar Yedla. He is a professor at Indira Gandhi Institute of Development Research, IGIDR, a Reserve Bank of India funded national institute and deemed university in Mumbai. He is specialized in environmental engineering and policy. He is an acclaimed teacher and researcher with 23 years of teaching and research experience and a strong publication record both in the top international journals such as American Society journals and other top league economic and development journals and books and book chapters. He served as Vice Chancellor of Dravidian University, Kuppam for the last term. His research focus includes climate studies, urban environmental management, sustainable cities, sustainable mobility, waste management, provision of urban services, study and development of eco-industrial parks, environmental economics, valuation of environmental services and assessment, and socio-economic impacts and the development. Professor Yedla has won 11 prestigious national and international fellowships and also won awards such as Fast Track Young Scientist Research Grant of DST, Government of India, Fellowship for Best Paper from Jeff of World Bank and Alexandria, Egypt, Best Paper at UN WIDER, Helsinki. Papers were rated 4th and 9th most downloaded article from Elsewhere's top 25 by Elsewhere publisher. He has been regularly on the who's who of global scientific and engineering fraternity. So as a whole, he is a very nice human being and is a scholar of environmental engineering and policy. So he was here in the year 2012 to deliver a lecture on the green construction and sustainability. So where we have organized a program on green construction compulsion of the day. So a national level faculty development program sponsored by AICT in the year 2012. Sir, again, so I welcome you, sir, to this FDP after almost 8 years. So the second FDP is on the same lines, sustainability. So thank you very much for your valuable presence, sir. So now I request you to take up the session, sir.
Thank you. Thank you, Professor Reddy Garu. It has been great pleasure getting associated with you. Time flies. A lot of time has passed since I visited you, but I had a good fortune of meeting your honorable chairperson Mohan Bab Garu in Hyderabad once, and he said you are most welcome to our institute anytime. And I'm very glad that within short time of that meeting, I could come and talk to people at Sri Vidyaniketan Engineering College. It has been a great experience visiting that campus, a beautiful campus, and beautifully architected and managed by eminent people. I definitely miss this opportunity of visiting the campus once again. Thanks to COVID, the world has changed now. So anyway, we are in a virtual world where we have no eye contacts. I had to keep looking at here and there, and I miss that eye contact with the colleagues and participants. Nevertheless, we have to move on. So let me share my screen for the presentation.
You can share.
Yeah. VIP lecture. Here we go. So all of you can see the screen, Ishwara Garu? Can you see the screen now?
Yes.
Yeah. Shall I make it full screen so that
Yes,
you have
yes,
a better view?
yes, sir.
Okay. Now it's fine?
Yes, sir. Yes, sir.
I'm audible and it is visible.
Yes, sir.
Wonderful. So unlike last time where I spoke about green buildings, because basically I'm a civil engineer, so I'm working on sustainability. I have interest in looking at how green the buildings are becoming over time, and now I'm very glad that the previous speaker has spoken about that. So this time I'll be talking more about the sustainability science as it is, what exactly constitutes the sustainability. And so within that, there is a concept of ecologically efficient production process, which is again an engineering domain altogether. And how do we bring this ecological efficiency in the production process, which is an integral part of sustainability as altogether. So, as I said, I'll be talking about the sustainability, what are the degrees of sustainability, the basic components of it, and what guides the eco-efficiency of production and the necessary conditions for eco-industrial parks, and the critical strategies that are required. Now, I would have loved to make it a bit more interactive, but because that doesn't happen here, let me do the interaction myself. Science of sustainability. Sustainability is an ocean. Reddy Garu, remind me when we have 10-15 minutes to close the session so that I can.
Definitely.
So sustainability is a big ocean. Everybody under the sun either works on it or claim to be working on it. And it always brings a question to young teachers and young researchers and students many times. What exactly is the system boundary of sustainability? So I always feel that it is necessary to introduce that system of sustainability, system boundary of sustainability, whenever we talk about sustainability on any lecture or on any occasion. There are philosophies, two different types of philosophies. So the general philosophies of sustainability, one is based on environmentalism, the other is based on the systems approach, the way we handle it. So when we look at the environmentalism, there are two concepts, two approaches, or other schools of thoughts, you can say. One is a strong sustainability principles based approach. The second is the weak sustainability principle based approach. Say, for example, as a policymaker, I would say that there is a woodland. I will cut down the woodland, convert that into a beautiful high-tech city kind of a thing. And then I'll pass on that endowment to the future generations. Like Honorable Chandrababu Naidu Garu says that it is created in Hyderabad, and then for future many decades, Hyderabad, the great endowment is passed on to next generations. That is sustainable. Sustainability is essentially passing on the endowment to the next generation with a greater ability for them to enjoy whatever they want to enjoy. They say, we have created this and pass it on to the next generation. They say it is sustainable. That is a weaker sustainability in concept. Why? Because we are assuming the perfect substitutability of the endowment, meaning to say you are saying there is a perfect substitution of this so-called artificially created wealth, whether it is high-tech city or huge industrial park, whatever it is a perfect substitution for whatever was there earlier. And we have destroyed a wetland. The strong sustainability principle says any new endowment created by human beings cannot be a perfect substitution for the environmental endowment that is in place. See, that is a stronger sustainability principles. Both have sustainability argument, but the stronger sustainability refuses the perfect substitution of capital. So that drives the philosophy of environmental, based on environmentalism, philosophies of environmentalism. Once we decide on that, then comes how do we approach the system's approach to sustainability? How do we make systems sustainable? There is a concept of internal sustainability and external sustainability. You see, if I move on to the next slide, if you take a city as a black box, city is a system, okay? The system is treated as a black box. You don't worry about what happens in the black box. But as long as you can supply whatever is required for this black box to perform, and whatever comes out of black box as waste or byproducts, whatever it is, and environment is able to take that, as it comes, environment is able to take that without getting impacted. Then you say it's a kind of external sustainability condition. You see, system is your black box, but the external supply and external receipt of the waste is maintained. Means externally the system is sustainable. Of course, such external sustainability condition is limited by the principles of limits to growth. But then there is other way of approaching sustainability in the system is make this so-called black box, more efficient. Okay, so that the resources are used in a much efficient way, and that makes it sustain the system longer. And that's called internal sustainability of the system. So resources coming in, resources going out, if that is maintained sufficiently, it is external sustainability, system is externally sustainable. If you make the internal system also very efficient, that becomes internal sustainability condition. So what happens in this black box is basically this interaction. Any economist and working in the environmental area knows this diagram very well. The three spheres of economics, social dimensions, and environmental aspects, they interact actively in the system. And such interactions, the intersection of economics and society gives you the distributional efficiency. And economic and environmental interaction gives you long-term allocation efficiency. And society and the environment gives you equitable environmental equity on that. So the condition for sustainability of these interactions, which is basically the black box that we talked about here, is the positive externalities coming out from these interactions should be larger than negative externalities resulting from these interactions. That essentially makes the black box very efficient. See, putting that in the perspective of stage model, as explained by the Far East countries like Japan and Korea, where the environmental problems keep changing as the country progresses economically. When the country is in poor condition, we have a stage 1 related environmental issues, which fades away with the country progressing further by means of emphatic production activity, leading to production-related environmental issues. Further economic development will take the country further on environmental progression, and they start having issues of consumption-related environmental issues, wherein the production-related environmental issues will disappear. The new set of environmental issues will come here. So these are the three stages, and subsequently the eco-city stage, where you don't have much of environmental issues altogether. So when the countries which are in production-related environmental issues, facing production-related environmental issues, they will be uh, at a stage where they should address the internal sustainability more seriously, because the endowment is not an issue, endowment of resources, because resource consumption is not a big issue here, but efficiency of the system, whether it is industries or a city altogether, one has to address this internal sustainability at this stage of environmental model. And as you move on to the next stage, then you have a chance of addressing or need of addressing external sustainability condition, which is resources endowment and waste handling put together. So we can say industrialized countries are more to do with external sustainability. They need to manage their consumption patterns better. Developing countries must focus on attaining internal sustainability. Let me remind you here once again, only addressing either internal sustainability or external sustainability would not give you the pathway to sustainable development. We both have to be handled in tandem together. But the context here is when a country is developing, their focus should be more on this, apart from addressing the external sustainability, but priority is on the internal sustainability. Whereas in industrialized countries, because their systems are already efficient, they have to focus more on external sustainability condition where consumptions are reduced, per capita consumptions or whatever. Okay, now putting them together, I moved on to the next slide. I hope it is moving on your screen as well. So we have two components in ecologically efficient systems. We can call them eco-efficient cities. One is eco-efficient production. The second is eco-efficient consumption. See, now as we all see, the consumption needs behavioral changes. Consumption has to cut down, conservation of resources has to be taken up. But then when you have affordability, you never try to conserve. See, but thankfully, I would rather say thankfully, COVID has taught us on how to conserve our rations. Now we don't create too much of food waste. Now we don't unnecessarily consume with a fear that there may be shortage of grocery or whatever. So we have been introduced to glimpses of behavioral change of consumption patterns. It's not behavioral change as yet, but there are some changes which can be transformed into larger picture of behavioral changes. So we are writing a paper for Korean Institute of Economic Policy on that, on how these small changes can be cascaded into much bigger transformational changes on consumption pattern. Coming back to the present topic here, consumption pattern is one thing which happens at individual levels and the system levels also. But eco-efficient production is something which is very focused. As we're all engineers, it is all pointed thing. Production happens in particular pointed industries. So in today's lecture, I'm actually concentrating more on this eco-efficient production, leaving aside eco-efficient consumption. But let me remind you once again, eco-efficient cities or eco-efficient systems need to have both these components together. Okay, moving further, what defines the degree of sustainability? Essentially, the systems have to be circular. Let me go to the next slide so that it will be more clear for you. Yes, linear metabolism, where resources come in and whatever comes out has nothing to do with the resources coming in. It simply goes out. It is a linear system of metabolism, which is inefficient. And then we have something called circular metabolism, where resources come in, they get processed. This is the system that uses the resource, and something comes out of the system. Law of conservation of energy or material, whatever you call it, you can't destroy anything. It only transforms into something else by products and waste products, apart from the products which the system enjoys. Then those can be recycled into the same system, some of them. Some can actually go and become available for other systems to use as inputs. So this is a kind of circular metabolism. If I go back to the previous slide. So circular metabolism, every output can also be used as input elsewhere. either within their own system or in some other system, but it is used elsewhere. It is not simply sent out as waste. So it is important to get onto this circular metabolism from the systems of linear metabolism. Now, all of you must have heard circular economy. The Japanese, Koreans, and Chinese have been embarking that too for quite some time now. And India is on its way to embark onto circular economy systems, circular economies. So this is going to play a crucial role in production of the production sector of the country. Now, what is this? What is this circular metabolism? Here comes. The nature is beautiful. If we have two independent species, biological communities, whatever you call it, they are otherwise independent. They can exist on their own, but they coexist in such a way, they do these exchanges in such a way that the exchanges can happen in the form of materials, it can in the form of energy, it can in the form of supporting the living thing there. Basically, they get benefited in such a way that the total benefit of the system of ecosystem that they have is bigger than the individual benefits that they accrue. So they are otherwise independent, but they coexist. That forms a symbiosis in the metabolism process. So that's called symbiosis. Now, industries trying to mimic that particular concept of two industries which are otherwise independent, they try to get together, share certain things, and draw maximized benefit out of it. That's what the industries try to mimic from the nature systems. That's called industrial ecology. We have natural ecology, ecological systems. Then industries get into that kind of ecological system where symbiosis happens. First of that kind happened in Denmark, called Kalundborg. It's a small town in Denmark, Kalundborg municipality. The condition, as I said, they exchange certain things among firms, and these network linkages lead to higher level of benefits. And one precondition for industrial symbiosis to be called symbiosis is the collective benefits of the firms should be much larger than the sum of individual benefits of the firms. That's the precondition for any symbiosis to exist, whether it is industries or nature. And based on this Kalundborg, this is a beautiful Kalundborg thermal power plant that they have there. And this is the exchange that happened in Kalundborg. I hope all of you are able to see this flow chart kind of a diagram of Kalundborg municipality. Industrial ecosystem at Kalundborg, Denmark. They have electric power station, and they exchange certain byproducts and waste products with other entities. For example, they send their waste steam into oil refinery. They use oil, this steam as input, and they send volatile ashes to cement factory, as they use these volatile ashes as input in cement factory. Otherwise, these are all waste that needs to be handled by power station. Then waste heat gets to fish culture. From there, sludge goes to local farmers to act as fertilizer. Then waste heat from power station goes to municipality of Kalundborg, where they need centralized heating system. It goes and joins that system. So they have a number of industries and other activities like fish culture and local farmers, pig farmers. They actually try to use their byproducts and waste products as input material in other entities as such. So this is the first industrial park that has been developed. It has happened over a period of 50 years, more than that. But this is the first demonstrated eco-industrial park in the world. All right. So of course, this presents the previous slide in a more pragmatic way. Moving further, they have demonstrated a certain benefits which are very, very attractive to everyone to follow. They could avoid the fly ash and clinker, about 200,000 tons of fly ash, which has to be released into the environment, or use it as deposit or store it in the firms, power stations, that was used as input material. So they have avoided this much of waste. Scrubber sludge that comes from industries, 80,000 tons was avoided. These are per year numbers. Sulfur is this much. Water treatment sludge, 1 million cubic meters of water treatment sludge was avoided from treatment requirements. So, and similarly, annual savings also they calculated. As you can see, 1.2 million cubic meters of water as a resource was saved, and 30,000 tons of coal was saved. 19,000 tons of oil was saved because. So these are all the extremely large benefits that they demonstrated in Kalundborg municipality. Now, this eco-industrial park, as I said, is picking up momentum in the world because the industrial production is becoming more efficient there. Unit cost of production comes down because they don't have to treat the waste material, and also they don't have to draw original resources which are expected to be expensive compared to the recycled material as input. So as a result, the production cost, unit cost of production is coming down in the industries, and that makes them better off. So there are 250 self-styled eco-industrial parks operating today, and the progression happened fairly quick. There were only 50 in 2000 a year, and by now it has gone to 250, which is supposed to be good progression. So EIPs offer business advantages, as I've been telling you. There are many improving productivity issues are there, more efficient use of resources, and meeting social responsibility goals, lowering the exposures of climate change risks and all that. But it is still in the development stage. It's not completely developed, completely evolved into implementation in the world, in different parts of the world. It is fairly in place in eastern part of the world. So, of course, the World Bank and other larger groups have got together. They identified the importance and potential of eco-industrial production. They try to make certain framework of EIPs. And then one of the first ones to embark onto EIP, eco-industrial park, meaning to say converting their existing industrial parks into resources conserving eco-industrial parks. And that's what is done by Maipo Industrial Park in Ulsan, Maipo, and Onsan Industrial Park in South Korea. As you can see, these are all industrial parks along this coast. All these are industrial zone, and they have made a national policy to convert their industrial parks into eco-industrial parks. And so these are the number of profile of 5 EIP sites in South Korea. And as you can see, they have identified large areas as eco-industrial parks, meaning they're converting the industrial parks into eco-industrial parks. And as you can see, Banwal Silva site has almost 7,000 companies operating there of different nature, SMEs and manufacturing. And Ulsan and Maipo, as I mentioned, have more than 1,000 companies in much larger areas, spread over a much larger area. They have large companies, heavy industries, oil refineries, etc. So they have been attempting in a big way to convert their industries into eco-industrial parks. What happens in eco-industrial parks? There are different types of clusters. They can be clusters of similar industries like textiles. They coexist and the exchanges can happen there. And they can be of different industries. Is there somebody trying to talk to me? You are muted.
Yeah.
Am I audible?
Yes, sir. Yes, sir.
I got disconnected just now or sometime back?
No, just now some noise is coming. That's why I muted everybody.
Oh, wonderful, wonderful. Yeah, so the Simba exchange can happen in 2 different types. One is similar industries coexisting, like tanneries in Kanpur, textiles in Gujarat. And other type of exchange is the clustering is different types of industries. As you have seen in the case of Kalundborg municipality, we'll have different types of industries coexist and exchange things. An example is the Onsan Industrial Park and then Kalundborg, as I mentioned to you. Yeah, so an industrial park essentially is a community of manufacturing and the services businesses located together on a common property. Member businesses seek enhanced environmental, economic, social performance through collaboration in manufacturing, as well as managing environmental and resources issues. So by getting together, the community of businesses seek a collective benefit that is greater than the sum of individual benefits, as I explained you before. And this is the formal definition that the World Bank and other groups got together tried to give. And the Ulsan EIP is one such entity which is trying to get onto, which is trying to become an EIP from the existing parks. And in those EIPs, the exchanges happen in the following ways. Exchanges through ways, like ways are being exchanged. That's the type 1. Type 2, exchanges within a firm from one unit to another unit kind of a thing. And the third type is exchanges among firms co-located. Like in case of Onsan, as I showed you picture, they're all co-located. They're different firms, but co-located. That is the third type. Exchanges among local firms that are not coexisted. For example, there's a firm in, say, Tirupati, the extreme end of Tirupati, and there's another firm in more closer to the Chennai border, for example. They can also exchange. That's a type 4 exchange. And the type 5 is there's no border region that across the borders they still exchange things. There are different types of exchanges that happens in industrial symbiosis. And as I said, they try to see a larger picture, a cost savings they try to attempt, a reduce infrastructure development cost they try to attempt by this, revenue generation they try to attempt, and improve human resources, and newer investment opportunities, and access to newer technologies. So these are all the benefits they look at when they try to embark onto eco-industrial production. Now, as the industries coexist, there is a possibility of exchanging between one industry to many industries. And depending on the cost of that exchange, only some things are more beneficial for the firm to exchange. And it is very important to identify what are those firms that gives the maximum social benefit in exchange instead of going to some other firms in exchange. So it is important to identify all possible links and then identify what are those links which are more feasible economically and more viable socially. So for that, we need to find the optimal links of symbiosis within the industrial network. And that's what are going to, so I was in Nipo Industrial Park. I worked as part of the team, the national EIP development team in South Korea. I was part of that. I was there for a year and a half. I worked in Onsan Industrial Park. So we developed this framework of optimization, how to optimize eco-industrial networking for sustainable development. I'll take you through that. Now, if a firm FE has the possibility of networking with firm FA, firm FD, firm FB, and firm FC, the same material can be shared with these firms. And now FE has to decide whether to go ahead with FD or share with FB or with other two. What defines that? What defines is the following. There are inputs, energy, water, raw material for any industry. And there are outputs that are the product, intended product. And there are certain byproducts in case of power stations, fly ash, for example. And there are certain wastes. It can be wastewater, solid waste, whatever, but waste. And what are the costs involved in production is cost of energy, cost of water, cost of materials, and the cost of byproduct and waste treatments and discharges. If byproduct has to be stored, that incurs some cost. If the wastes have to be treated, they also incur some cost. So that also becomes part of the production cost. So with these inputs, as you can portray them in a pictorial way, firm A has inputs and outputs. Firm B has, again, these inputs are common. Outputs could be slightly different for n number of firms in the industrial park. Okay. Now, as you can see, limiting factors for networking is cost difference between the virgin material and the byproduct stream. I'm sorry. So the cost, say for example, if you want steam as an input material for your industrial process, generating the steam by means of a boiler is the original process. And that is expected to be costlier than borrowing steam from a neighboring industry. Okay, that's a condition. Cost difference between virgin material and byproduct stream is actually the limiting factor for networking. So the cost of production is a function of transportation, cost of using these materials into production, purification process, scale of operation, number of firms contributing to the supply of byproduct. So this cost I'm talking about here is a function of these factors. Moving further, so minimizing per unit production cost of industrial cluster under consideration is what we're trying to do. And here we consider only resources cost, excluding labor and capital, because they don't change much. They remain the same, but resources cost will change. So that's what we're going to try here. The marginal production cost per unit is basically, marginally means per unit cost, is cost of input material, cost of energy, cost of water, and cost of waste and byproduct treatment and discharge. This is the summation of all this. So that gives rise to marginal production cost of a firm, a single firm, is the summation of CM, CE, CW, and the summation of C waste. And if you make that for a cluster, marginal production cost of the cluster, having n number of industries, you have the summation over I to n of all these individual costs that we talked about. Again, summation of 1 to n, all the waste costs, waste treatment costs that we have. Moving further, the cost of energy required per unit output is calculated as quantity of energy, that is QE, and cost per unit energy, that's CE. So we have this equation in place. Similarly, cost of water required per unit output is cost of water comes from quantity of water required and cost of each unit of the water resource. And so is for materials required. So these three are the inputs for any industry and all industries in the unit, industrial part. So the cost of waste treatment required per unit, this is also part of this explanation. Then we have marginal production cost for the cluster put together comes as QEI multiplied by cost of unit energy. This is the quantity of energy required for each industry. So you're summing it over all industries here. So this is the marginal production cost for the entire cluster expressed in the form of quantity of energy required to produce one unit and a number of units, of course, you would declare. And cost per unit of energy is given there. So the byproduct of a firm I can be used as energy in another firm J, meaning to say if there are n firms, the source of byproduct as input material is only n minus 1. So the byproducts from firms, number of firms M can be used as energy in a particular firm I. So similarly, byproduct streams related to material and water can also be used. Same explanation applies. I repeat once again, for firm I to use all other firms byproducts as input, only n minus 1 firms will be available to supply the byproduct. The total number of firms are n minus 1 firms will supply a byproduct to any particular firm. So taking that, here the marginal production cost for the cluster is, this is a quantity, individual quantity required and cost of energy. So you draw resources from firm J equal to 0 to M. So M is n minus 1 and J equal to 0 indicates the source is virgin material. If J is 1 is from firm 1, J is 2 is from firm 2. So it goes on till M. So you sum it over. So we have production quantity required and cost for energy, quantity required and cost for material, and same for water. We sum it over, and this energy source is again distributed. Energy coming from J. So this will be summed over number of firms contributing energy as a source, and then it will be summed over all firms that you're talking about. And here, Q waste means quantity of waste generated minus Q recycled. How much ever waste is recycled in any firm. Recycle means maybe given to some other firm as energy source or material source. That is deducted from this firm's total waste generated, and that is multiplied with unit cost of waste treatment to get the cost of waste treatment as part of the production cost. So the marginal production cost of a cluster is portrayed like this, and the explanation that I gave just now, the quantity of energy drawn from by firm I from source J is QEIJ. Similarly for other inputs, and the CEI, the cost of energy from source J. Sorry, this is CEJ. CMJ is cost of material from source J. For example, firm 1, cost of material could be different from firm 2. Meaning to say, the material that is coming out from a firm that is to be used as resource or input material for some other firm, there is a cost involved in this. Maybe it has to be transported, and maybe it has to be purified, maybe it has to be processed a little bit. That's the cost I'm talking about. And that is different from individual firms. So they take that varied cost here, and then quantity of waste treated in firm I is this, and Q recycle I is quantity of waste recycled in firm I, and the cost is C. Yeah. Now, if you put that, put this marginal production cost function for optimization exercise, we have to talk about minimizing the cost of objective, minimization of the objective function, basically minimizing the cost of unit cost of production in the industrial cluster altogether, with the variables of quantity of energy, material waste used from different sources in firm I. So how much of E, say for example, firm I requires n number of energies of n number of units of energy. Out of that n units of energy, how much should come from firm 1, how much should come from firm 2, how much should come from firm 3 is what is going to be output of this model. Subjected to certain conditions, let me check the time, we have 10 minutes left. So subjected to certain constraints where QEIJ is greater than or equal to QEI. What does it actually explain? The total energy drawn from different sources is J here, okay? Total energy drawn from different sources should be more than or equal to the total energy required to produce a unit output from the firm I. Capital QEI is the total energy required for firm I for its production process. So the total energy drawn from different sources should be greater than or equal to QEI. Otherwise, the firm I cannot meet its energy requirements. That's a condition one has to satisfy. And similarly, for water and material, you apply the same constraint. Total water drawn from different sources by firm I should be greater than or equal to the total water required for firm I to produce the goods that they wanted to produce. Same applies to material. Another constraint required here is the total quantity of energy drawn from all recycling sources, energy drawn from all recycling sources, J equal to 1 to M here, should be less than or equal to the total waste or byproduct generated in all firms. Meaning to say, whatever we are drawing, see, we are drawing energy from different, say 10 different firms. And whatever we are drawing from those 10 different firms, their waste or byproduct streams as energy source for number of firms should be less than or equal to the total such thing generated in the park. Okay. So the total such thing generated in the park is for all industries together, and quantity of energy drawn from all recycling source. Recycling source can be only n minus 1, that is M. So it should be less than or equal to this. Otherwise, the condition for requirement of the material would not be met. Meaning to say, condition for requirement of recycled material from different firms to be used as resource material would not be met unless this constraint is satisfied. So the data set required for this kind of optimization exercise is the quantity of energy required per unit of production in different firms, and the quantity of waste generation per unit of production in different firms, and of course, cost of unit of energy from virgin source. If steam is the energy, what is the cost of generating the steam by boiler is the virgin source. Cost of unit material from virgin source and so on, then cost of unit waste treatment original in all firms. Then most importantly, cost of unit of energy from other sources. If you want to bring steam from thermal power station to refinery, what's the cost of that transport or process, whatever it is? That cost has to be, that becomes the cost of unit energy there. And so once we have that, the output of the model is share of energy used from different firms and virgin source put together, meaning every firm, how much of original energy source is required and how much of other energy coming from different firms. Those links will be given by this model. Similarly for material and water as well. So this is the output from this model, and this gives optimal utilization of byproduct stream for recycling. So such a thing can be applied to any industrial park. So this was developed when I was there in the South Korea as part of that EIP development team for government of Korea. And yes, it was applied. Based on this, they have identified certain links in Maipo and Onsan Industrial Park in South Korea, and they have implemented 197 such links from one industry to another industry, some exchange of energy, there are some exchange of water, there are some exchange of material. So such 197 symbiotic links have been implemented, which came out from this analysis that we have done. And economic benefits are huge. Investments have gone up like $623 million. And there were significant cost cuts in the industries because of the symbiotic links, which is about $746 million US. And the new revenues have stemmed up, which is again huge in number. That is the targeted benefits for the industries. And then environmental benefits. There's a huge energy saving that happened, 1.35 million tons of oil equivalent. Then byproducts, they have been used in different processes, 5.21 million tons, which otherwise would have to be treated by those industries. Then huge water savings happened. Then carbon dioxide reduction also, 6.48 million tons of carbon dioxide was reduced. Same with oxides of sulfur and nitrogen. And then new employment was also generated. 848 people were induced in addition to what they were having earlier. So that's a new employment generation possibility there. So these are the economic and environmental social achievements of Korean EIP program, which use the optimization approach that I have explained it just now. So they are going in a big way in South Korea. Huge employment generation possibilities they are trying to look at. These are the benefits that we are just talking about. And of course, there are barriers. One of the most important barrier that I came across while working on Korean EIP is the lack of clear indicators or international benchmarks to guide the process. It is yet to be developed. What are the standards for such exchanges? But then I try to explore what are the critical strategies that are required for these EIPs to successfully be implemented. Then I found, and of course, along with my co-authors, one important thing is the risk. When an industry depends on other industries to supply the input material, there is always a risk. What if they fail to supply? You see, one fine day they find this, I'm flourishing as an industry very well, and they wanted to somehow, in a competition, they want to cut down my progression, and they simply cut down their supply of their byproduct, which is a input material for me. So such a risk has to be controlled. So future relocation or closure of industries which are providing their byproducts or waste streams as feedstock for other industries, it needs to be regulated. That's one of the very, very important condition for EIPs to progress. That's what was expressed by those 1,000 industries. We have conducted a survey in MIPO Industrial Park. Comprehensive material flow matrix at park level. If you have understood the data requirement for this optimization exercise, you would understand you need entire detailed process of every industry. What material is going in, what energy is going in, what water is going in, at different levels, what is coming out, because industrial process has segmented process lines. You need to have the entire information with the system boundary of the industrial park. And that analysis is termed as material flow analysis. It's upcoming topic now in engineering discipline, industrial engineering. So we need to have a comprehensive material flow matrix at park level for this EIP to progress. And this material flow matrix, yes, I'm almost done, Reddy Garu.
Yes, sir.
Yeah. So this material flow matrix actually provides the basis for this optimization exercise that I have just explained. And that's also essential for industrial park to progress. Then, as you have seen in the last slide, there are a lot of investments that happen, about 1,000 million US dollars in the particular industrial park. That happened in a framework of partnerships. Public-private partnerships are very, very essential for industrial, eco-industrial production to progress. That has to be ensured. Integrate environmental regulations. I'm sure all of your engineers and some of your environmental engineers also. In environmental engineering, you would have come across that hazardous waste cannot be recycled, okay, for obvious reasons. In the name of recycling, they can avoid treating hazardous waste, and that leads to a lot of complications. So in order for industries, because most of the industrial solid waste, sometimes liquid waste, is hazardous in nature. So the existing regulation that you cannot recycle any hazardous waste stops industries from attempting these exchanges that they're talking about. So there needs to be an integration of environmental regulations into these EIP regulations at firm level. And of course, extended producer responsibility and the implementation of economic instruments brings in a lot of efficiency in production as well. So that provides the eco-efficient industries and eco-culture concepts put together. That finally, eco-efficient industrial networking presents multiple benefits, as this slide shows you. Control over environmental pollutions, as demonstrated by MIPO industry. Reduction of greenhouse gases, employment generation, reduce energy intensity of the production, and increase the production also, and reduce the production cost. So it is important to account for all these benefits in the form of co-benefits, so that the claim for progression of eco-industrial production or eco-industrial networking based production can take place. So the co-benefits is the good framework to integrate the so-called climate change strategy, climate protection strategies with eco-efficient production strategies. Eco-efficient production strategies give a lot of climate benefits, a lot of pollution benefits. So if you account for those, there is a possibility of drawing funds from climate funds that are available for eco-industrial networking as well. So this integration is going to be the key. So yes, eco-industrial networking is taking up in India also. All of you must have heard special economic zones. And of course, when in the erstwhile United Andhra Pradesh, when Jayesh Ranjan, Mr. Jayesh Ranjan was the in charge of industries, we did had a long discussion on how to convert these special economic zones into ecologically efficient production zones. And many state governments are working on it. Ministry of Environment and Forest is also developing a framework for implementation of eco-industrial parks in the country. It has a lot of potential, a lot of energy saving abilities. And as if you remember, ecological efficient societies need consumption, ecological efficient consumption, ecological efficient production. Production can be taken care by eco-industrial networking. Consumption, of course, as I said, needs behavioral changes. I think I'll stop here. I thank Professor Reddy for giving this opportunity to share my views on eco-industrial production and ecological efficient societies in general, and how eco-industrial production adds to sustainability of the society. And thank all the audience for patient listening. If any one of you have any concerns or want to have further augmented discussion or learning or share exchange of material, you can write to me. My email is sudhakar@igidr.ac.in. So of course you can get it on my website as well. If you type Sudhakar Yedla, it will come there. I look forward to having more interactions with the participants, not necessarily here, but subsequent to this discussion. Thank you once again for patient listening.
Thank you, sir. Sir, if anybody has questions, you can raise your hand so that Professor will answer. You can post your questions in chat session also. Sir, I have a question, sir.
Yes, sir. Please
yeah. So after listening to you, so I have a question regarding industrial parks establishment. The industrial policy of governments will make a lot of difference with regard to sustainability is concerned. So prior to the establishment itself, if you could able to plan the industrial parks with a vision to have sustainable networking. So as your lecture is completely on that, is it possible, sir, for the governments?
Yeah, as I said, there was a discussion with AP Pollution Control Board Chairman Prashad Garu that as the state is newly formed and trying to promote industrialization, they try to map the entire state and identify locations that are more suitable for certain types of industries altogether. So if a particular zone having water, and that zone is suitable for industries which require more water supply, for example. There are some industries which require agriculture sector augmentation. So you can identify some areas, some lands that are available in the vicinity of agriculture land use, and those lands can be earmarked for industries that require more of agriculture augmentation, agriculture support. So that kind of mapping is a first step towards what we're actually trying to tell. Once that mapping is done, then it is possible to develop a special economic zones, as they make now, and government of India is trying to call them what do you call that? Smart cities. But I would rather say sustainable cities, wherein any industry has to be established in a designated area, and that can be done by the government once they map the entire state for suitability of different industries and provide the basic things. For example, there's a land which is a surplus water supply is there, and then we can possibly have a thermal power station there, and there is a mining also available in the vicinity. And so earmark that particular area with facilities developed that are required for thermal power station to come up, and along with that they can identify different industries which can network with thermal power station effectively and promote those industries in that particular industrial zone. And that's what exactly has to be done, can be done. The new industrial policy unfortunately does not have a focus on these aspects, and I think state governments must focus on making this kind of industrial policies where the clustering happens to bring in ecological efficiency. Ecological efficiency is basically the coexistence of those industries should be beneficial at much larger extent than the individual benefits of the firms itself. So it is not happening, Ishwar Garu, to be precise in answering your question. At least in Andhra Pradesh industrial policy that came out recently, that doesn't seem to be happening. But there are discussions. I personally had a discussion with a couple of pollution control board chairmen in these lines. The mapping part they're actually considering. Special economic zones, making them more efficient is there in the paper, is there in their minds, but yet to come into the into action.
Thank you, sir.
Yeah.
I have some questions. Yes, sir. There are no questions from audience.
Okay.
So I thank you once again, sir, for your valuable lecture and insights on eco-industrial networking, as well as how the sustainability has to be achieved through this networking. So if efficient networking is done, automatically the sustainability will be achieved to the maximum extent. So,
Yeah.
so I understand, sir, but at the same time, the waste products that are generated from the industry can also be utilized these networking industries. That concept also can be helpful. So I thank you for your valuable insights. So with a case study. So thank you very much, sir.
My pleasure, and wish you all a good time in the remainder of the program.
Thank you very much, sir.
So I'm signing off now.
Yeah, thank you.